So welcome to another video, and in this video we'll discuss about calculation of the MOR for singly reinforced beam. So let us write down the given quantities. B is equal to 300 mm, that is width, and effective depth D as 450. Similarly, characteristic strength as 20 Newton per mm square, and yield strength of the steel is 415. We are provided with two types of steel, one 25 mm and another is 20 mm. Now AST1 and AST2 be the area of steel for 25 mm bar and 20 mm bar respectively. Now for calculation of AST1 and AST2, these two steel are provided in the tension zone, so AST1 and AST2 acts as a combined reinforcement for tension zone. So AST is equal to AST1 plus AST2. We get 1610.066 mm square. Also, for the depth of neutral axis, at neutral axis C is equal to T, and for the compressive force we have 0.36 FCK B into D and 0.87 FY AST. Make sure that D is the depth, and for up to neutral axis it is XU. So 0.36 into 20 into 300 into XU is equal to 0.87 FY is 415 into AST, that is 1610.06 as a combined reinforcement. Now for the depth of neutral axis, XU is equal to, on solving we get XU as 269.126 mm. This is the actual depth of neutral axis. Now we have to compare with the limiting depth of neutral axis. From codal provision we have XU limiting is equal to, from the code you can see that is 0.479, which is nearly taken as 0.48 D, that is D is effective depth. We have already discussed about this in the previous video of LSM, introduction to LSM video. Link is given in the description. Since the limiting depth of neutral axis is less than that of the actual depth, so it is an over reinforced case. Now for the case of over reinforced section, MOR cannot be calculated by using the actual depth of neutral axis, so we have to use strain compatibility analysis for the calculation of MOR. We have to go through a series of trial to calculate the actual depth of neutral axis, and by comparing the assumed depth of neutral axis and calculated depth of neutral axis, when these two values come to be similar, then the depth of neutral axis is taken as the calculated values. For initial case, let XU is equal to 269.216 plus 216 divided by 2 is equal to 242.36 mm. We have to calculate the strain corresponding to the value. Now, as we know, for a over reinforced beam section, the actual depth of neutral axis is greater than that of the limiting value, and extreme value of strain in compression is 0.0035. D be the effective depth. Then applying similar triangle properties, we can find this value as 0.0035 D minus XU divided by XU, ESC being the strain. So substituting D as 450 and XU as 242.36, we get ESC is equal to 0.00299. Now from the SP16 code at page number 6 from table number A, we have to calculate the stress corresponding to the strain calculated. We are using 415 Fe415, so this table has to be used, and the value corresponding to ESC lies between 0.00276 and 0.00380. So from the linear interpolation we can calculate the value of FST for 0.0029. so for interpolation we have formula y minus y1 is equal to y2 by y2 minus y1, x2 minus x1 into x minus x1. So as we have to find FST, so consider FSY as y coordinate and EST as x coordinate. So substitute the value, and finally we get the value for corresponding to 0.00299 as 353.81 Newton per mm square. Now XU has to be calculated using the formula as we used previously, 0.87 FST AST 0.36 FCK B. But as we said, it is a over reinforced section, that is concrete fails much more before, so it is not necessary to provide partial safety of factor to the steel. gives us 263.73 mm. Now we have to check the value of XU calculated and XU assumed. XU assumed is 242.36 and calculated value is 263.73 mm, which is not similar or which is not nearly equal. So we have to go for another trial. Now going for another trial, XU is equal to calculated value and previously assumed value. So 242.36 plus 263.73 divided by 2, which gives us 253.04 mm. T is equal to 0.0035 d minus XU divided by XU. Again substitute the value of d, that is effective depth, which is 450 mm, and XU, which we have calculated just now, that is assumed value 253.04. so it gives us 0.00272. Now we have to calculate the stress corresponding to 0.00272 using linear interpolation. We can find the value of EST. Now again we have to find XU, that is actual depth of neutral axis. So substitute the value of FST. Now we get 261.464. Now comparing the assumed value and calculated value, these are much more nearer, but at least we can go for a third trial. So again XU is equal to previously assumed value plus calculated value divided by 2, that is average value. So it comes to be 257.254 mm. Now EST, which can be calculated by using 0.0035 d minus XU divided by XU, we get it as 0.00262. Now stress corresponding to 0.00262 strain, using linear interpolation from the table 6, we get FST as 348.2 Newton per mm square. Now again calculating the depth of actual neutral axis, substitute the value of FST and we get XU as 259.54. Now the calculated value and assumed value are nearer to each other or are nearly equal to each other. So taking XU as 259.54 mm, the calculated value, now we can calculate MOR. For Fe415, MOR can be directly calculated as 0.138 FCK BD square. But in this case, XU is not in relation with the effective depth, that is XU by D is not 0.48. Hence, we have to use 0.36 FCK B into XU into D minus 0.42 XU, and finally we get the value for MOR 0.36 into 20 into 300 into 259.54, 450 minus 0.42 into 259.54. Finally MOR is calculated as 199.72 kilonewton per meter. So this is the difference between singly reinforced beam section with over reinforced case and under reinforced case. In case of under reinforced, the MOR can be calculated by using the value of actual depth of neutral axis, but in case of over reinforced beam section, the value of XU is calculated by using strain compatibility, as the actual depth is much more greater than that of the limiting depth. So this is the difference between these two sections, that is over reinforced and under reinforced.